All right, we're going to continue chapter number 6 with lecture number 2. And in this lecture, we're going to talk a little bit more about the natural rate of unemployment, and we're going to create a model. We're going to build a model for determining what that natural rate of unemployment is. So let's get started by defining the natural rate of unemployment. We could think of that as the average rate of unemployment around which the economy fluctuates. All right, that's a very good statistical definition of it. It's also what we might call the full employment level of unemployment. Full employment level of unemployment. Now, what in the world do I mean by that? How can I have full employment and unemployment? Well, if you think about it, nothing is ever fully employed. Right? You don't work all the time. Now, you have to remember, employed is considered working. Unemployed is not working. So technically, if you want to think about it this way, from a theoretical standpoint, when you are sleeping, you are unemployed. You must sleep at some point in your life. You can't go on, coffee forever, although coffee is pretty good. You can't go with coffee forever, and so you end up you have to have some downtime. You have to be unemployed for a certain period of time. Factories have to be unemployed for maintenance. Everything has to have a little bit of downtime. Nothing can be operational all the time. And so if we take that to the economy, there's a certain number of people who have to be unemployed any given period of time, right? What for? Well, for things like, for example, switching jobs. For things like retooling because their skills have become unmarketable. There's periods of time that you will just have unemployment because of transition and dynamic mobility amongst factors within the economy. So in a recession, we will see that the actual unemployment rate rises above this. Why is it rising above this? Because we've had a business cycle downturn. Business activity has decreased. People aren't making as much money, and so they'll lay people off. But those layoffs will be temporary. We call that cyclical unemployment, or unemployment that's driven by business activity and fluctuations in business activity. Right? That will go above it. In expansions, on the other hand, though, a boom or an expansion will have unemployment go a little below this natural rate. But in the long run, the economy is always going to gravitate back towards this natural rate of unemployment. So if we take a look at that, some different ways of trying to measure this exist. One of those is a statistical way of doing it, and that's to kind of filter off these short-run fluctuations, right? Filter those off so that we're left with the long-run movements in unemployment. And there's ways to do that. There's all kinds of cool ways. Everything from a simple moving average, where we just average the last 12 periods, or the last 24 periods, or the last 4 periods, and we just move over time, keep that average, to really cool things like state space models and Kalman filters and, Bayesian ninjas. The Bayesian ninja thing is a joke. That's referring to another YouTube video, not by me, but very, very cool, on Kalman filters. In any event, not relevant to this class, you're looking at it statistically. What we want to filter off the short-term kind of wiggles with kind of the more long-term movements. That's one way to do it. Another way to think about this is to think about it within the context of an economic model. All right, so we're going to create a macroeconomic model which will allow us to try to explain some of these determinants of this natural rate of unemployment. So rather than doing a purely empirical approach to it, where we take the data and try to get the data to just tell us what it is without any theory, what we're going to do now is, can we create a model that will explain what this natural rate should be? So this first model, the first thing we need to do is we need to go through a little bit of notation. Number 1, L is the number of workers in the labor force. Next, E is the number of unemployed or employed workers. U is the number of unemployed workers. Something very important to note. U plus E equals L. All right? In this model, we have unemployed and and employed, and the unemployed plus the employed make up the labor force. U divided by L is the unemployment rate. And we're going to have a couple more variables to realize, but we'll hold it there for just a second. Next, L is exogenously determined. Now let's talk about that word real quick. Exogenous, all right, so exo means outside. Genously, all right, comes from, I don't know what it comes from, but it sounds like Genesis, right, which means to create. So it's created outside the model, or determined or generated outside of our model. So the model that we're creating isn't going to tell us anything about the labor force and how labor force develops. All we know is, given this labor force, how is the economy going to behave? And number 2, during any given month, we have S % of employed workers become separated from their job. Now that's a mouthful. S is what we call the job separation rate, all right, or the rate of job separation. What that means is each period, right, and we're working with monthly data right now, so our model is going to be monthly, so each period is a month. In any given month, what happens? If S, say, equals 10%, so S equals 10%, then 10% of all those who are employed will, for some reason, become unemployed. They may quit their job, they may be fired from their job, but for some reason they become unemployed. F, little f, is going to be the rate of job finding, or the finding rate. This is the fraction of unemployed workers who find a job. S and F are both exogenous. So this finding rate, this separation rate, again, this is not determined within our model. All right, it's determined outside of our model, so we take that as given. So let's look at this graphically. Essentially what's going on is, and I don't like this picture because, well, it's not creative enough. We've got 2 houses, so let's draw a little roof on there, a little roof on there, right? These 2 houses, and we got 2 different types of people. And it depends on what kind of person you are as to which house you live. If you're an employed person, you live in the employed house. So if you have a job, you live over here in the employed house. And if you're an unemployed person, or you don't have a job, you live over here in the unemployed house. Now, one thing to know, L, the labor force in this model, is fixed. So we're not allowing for people to become discouraged, or they can't be in here so long they just drop out of the labor force. Right now, our L stays fixed, so we have no discouraged workers. We're not worrying about that. Okay, so you're either employed and living in the employed house, or you're unemployed and living in the unemployed house. Next, each month, some people become separated from their job. You know, they say, I just can't live under this roof anymore, and they move from the employed house to the unemployed house. So S times E are the number of people who become separated from their job. Okay? In other words, they were employed and now they become unemployed. Next, in a bit of very unfortunate notation, we find that the finding rate times the number unemployed find a job. So this number of people go from being unemployed to finding a job and are now employed. So we have a flow of people out of the employed house into the unemployed house. These are the number of people who are separated from their job, right? And we have a flow of people from the unemployed house into the employed house. These are those who find a job, right? And this becomes this dynamic system. So in month 1, this many people go to unemployed, this many people go to employed. Now we know what new employed, we know what the unemployed is. Month 2, this many people go from employed to unemployed. This many people go from unemployed to employed, and, well, over and over and over again. And so this dynamic system is going to keep moving, and employed and unemployed are going to keep changing until we hit something called a steady state. Now, what is a steady state? A steady state is where the number of people in the employed house, right, the number of people here stays constant. And the number of people in the unemployed house stays constant. So when we get to a point where the number of people over here in the employed house, the number of people over here in the unemployed house stays constant, then we've hit what's called the steady state. So where might that happen? Well, that's going to happen when the flow out of employed is equal to the flow in to employed. Or the flow in to unemployed is going to equal the flow out of unemployed. In other words, it's going to be where the number of people who are separated from their job every month, who lose their job, equals the number of people who gain a job, who find a job. So that gives us an equilibrium condition, but within a steady state, okay, this is called, or within a dynamic model, this equilibrium is called a steady state. Okay, so the steady state condition. Definition: the labor market is in steady state or long-run equilibrium if the unemployment rate is constant. Well, what does that mean? How does that relate to what we just said? Well, the labor force is fixed by our assumption. All right, we left that fixed because it's by assumption. And the unemployment rate equals what? Unemployment divided by the labor force. So if I want the unemployment rate to stay fixed, what do I need to have? I need to have a place where unemployment stays fixed. Where is that? That place where we're in steady state, or the flow into unemployed equals the flow out of unemployed, or S times E equals F times U. Okay, so moving forward, our steady state condition is right here. And putting this very simply, the number of employed people who lose or leave their job has to equal the number of people who find their job in any given month. So from that, how do we find a natural rate of unemployment? This is where the steady state, at least in this particular system, the steady state is where the economy is naturally going to gravitate towards. The economy is going to be pulled to this point in steady state. So if we get too much, our unemployment rate is too low, what does that mean? That means we have more people in employed house than what we can sustain, or the number of people in the unemployed house is lower than can be sustained in the long run. And so what's going to happen? Employed's going to fall, unemployed's going to rise until we get back to this equilibrium condition. Now, note, this does not mean that employed equals unemployed. This means the number of people who leave their job equals the number of people who find their job. So let's take this steady state equation and see if we can use that to find an unemployment rate. So the first problem with that is we want to find what? Unemployment, which is U over L. Now, if you remember that steady state equation, there was no L in it. But there kind of was. We just have to be a little bit sneaky. So let's rewrite this equation. All right, there's our steady state equation. But let's use a little fact. I know that L equals U plus E, which implies that E equals L minus U. Okay, well, let's go ahead and make this substitution. So I'm going to take this and substitute it in here. So let me write that out. Okay, now we have written our equilibrium condition, or our steady state condition, in terms of the unemployed, number unemployed, and the labor force. Okay, now we just have to algebraically manipulate this to solve for something that looks like, well, U divided by S. Well, the first problem I have is this silly minus is in the way. So let me go ahead and I'll do some manipulations, and you can see it in just a second. Okay, we've found our condition. So if we solve this for U over L, and it's just some algebraic manipulations, you can do all of those, we find that this natural rate of unemployment, which is U divided by L in the steady state, is equal to the separation rate divided by the finding rate plus the separation rate. So let's take an example. So each month, 1% of workers lose their jobs, are separated from their jobs. So S equals 0.01. 19% of the unemployed workers find a job, so F equals 0.19. Find the natural rate of unemployment. Well, I know that the natural rate of unemployment, let's call that UR sub N for natural rate of unemployment, equals, right, this equals S, which is 0.01, divided by 0.01 plus 0.19. Remember, S is 0.01, F is 0.19. This becomes just a matter of plug and chug, and it equals approximately 1 over 20. Or, actually it doesn't equal approximately, it is 1 over 20, which is 5%. So that gives us a 5% natural rate of unemployment. And there, written out a little more nicely, you see the exact same thing. Okay, so what are some of the policy implications of this? Well, basic policy implication is that the natural rate of unemployment will be reduced if we lower S or increase F. All right? If we can lower the separation rate, now this makes a lot of sense. If we can lower the rate or the percentage of student or a percentage of employed people who become separated, that should lower what? The natural rate of unemployment. If we can increase the finding rate, make people find jobs faster, that will decrease the natural rate of unemployment. And you can see that mathematically by simply taking the partial derivative of this natural rate of unemployment condition with respect to S or with respect to F. Okay, and that concludes lecture number 2.